All right, so this video is just for, I just want to be able to kind of collect a couple more thoughts about the integral test and try to sort of clarify some things for you guys. So yeah, hopefully this is helpful. The first thing I want to talk about is basically the sort of the important hypotheses. Like if you were to make a formal statement of the integral test, which we're not really doing, the book doesn't really do this either. And it doesn't make sense for us to do it in the sense that like we can't prove it yet because we haven't actually defined what an integral is. But if you were, once you get to the point where you define an integral, if you were to try to formalize this somehow, what would the statement look like? Okay, it would look something like this. So let me kind of make a formal, quote unquote, formal statement. Okay, so let an be a series and suppose there exists a function defined on the interval 1 to infinity such that f is so for the most important requirement obviously is that f of n equals an, okay, and f is non-negative decreasing and continuous. Then the series an converges if and only if the integral from 1 to infinity of f of x dx converges. So the convergence converges. The convergence is the same, okay? And remember, I can't emphasize this enough, that the series, the value of the series, if it converges, is not equal to the value of the integral, okay? They are not equal, all right? In general, they are absolutely not equal. I mean, they could be in some weird cases, but in general, they're not. So this collection of properties is kind of important. I think maybe the ones that are sort of relatively obviously necessary are this one, non-negative, and this one, continuous, just because it's kind of clear that if you drop the non-negativity, then all sorts of weird things can happen. I mean, if you keep the other two, then it's actually kind of like not really possible for you to get into a situation where f can achieve negative values, but it maintains the other two properties and then this still converges. Like that's not really possible. But ignoring that for now, the continuity is kind of necessary just because otherwise you could just have the values of f at x equals n. Those values could just be like unrelated to all the other values of f. So that's important. But what's really interesting is to think about what happens when you drop the requirement of the decreasing, when you drop the decreasing requirement. So what happens if f need not be decreasing? Let me just kind of sketch an example for you of what can go wrong. So basically, what you can have is a function which, so let's sort of plot some points here. So here's, let's say an equals 1 over n, right? The series of an, we know this diverges. Now, so here's x equals 1, here's x equals 2, here's x equals 3, here's x equals 4. And I actually encourage you to like pause the video and think about what can go wrong here before I explain it, okay? I think this is like a very good mental exercise. It's the exact kind of, It's the exact kind of exercise that I'm going to be asking of you guys in the near future, okay? So definitely take this opportunity to think about this yourself. But yeah, so I'll go ahead and explain it now. I hope you at least gave it a few minutes of thought. But what you can have if you don't require f to diverge is basically the graph of f could be something like this. So f is at 0, and then it kind of spikes up to this value, and then spikes up to this value, and then it spikes up to this value, and then it spikes up to this one. And it's supposed to be 0 everywhere else, okay? And basically, right, these little spikes here, so this is like, let's say this is 1, and this is 1/2, and this is 1/3, and so on, right? So it manages to hit each of these values at each integer on the x-axis, but at each positive integer, right? But what you can do is like you can design f, and I mean I'm not going to write out a formula because it's complicated, but you can basically just make these spikes be, you know, really narrow, and you can make them get narrower and narrower. So by making the spikes get narrower very quickly, we can cause the integral of f of x dx from, let's say, 1 to infinity to converge, okay? Because the integral is just like the sum of the areas under these spikes. So by just making these areas go down like, you know, 1 over n squared or faster, we can make the overall integral can still converge even though it's spiking up to these values of 1 over n, right? So now you can see that we've decoupled, you know, the convergence of the integral from the convergence of the series. They're different now, okay? And that's allowed to happen if you don't force f to be decreasing. So that's kind of why that's actually a necessary hypothesis over here, because otherwise, you know, stuff like this can happen. All right, so that's one little facet of the integral test that I wanted to clean up or sort of cover. The other thing I want to talk about is just like, what is the role of the integral test in a class where we place so much emphasis on building the theory from the ground up and always making sure that everything we do follows from what we've done previously, right? Now with the integral test, it's like all of a sudden we have this thing that's talking about something that we haven't defined at all. So if you're uncomfortable with that idea, I guess I'll say, so if the integrals in the integral test make you nervous, I want to say consider the test a heuristic, okay? And what I mean by that is it can tell you whether to expect a series to converge or diverge even if you don't use the integral test. So don't use it in a proof, okay? So obviously, you know, okay, for the exercises for section 15, of course you're allowed to use the integral test, okay? And I would go so far as to say that you're pretty much allowed to use the integral test for almost anything else in the class. The context should generally make it clear when you shouldn't be using the integral test, because the whole point of like being careful about this kind of thing is that the main thing we want to avoid, the main thing we need to avoid is circularity, right? So for example, using the integral test to prove integrals exist or something similar to that, right? Obviously, if you use the integral test to prove something, and then you use that thing to prove that integrals exist, or who knows what, right? There are all sorts of like circular connections that can happen, and that's the main thing that we try to be really careful of in this class. Is like we want to make sure we build the theory in this kind of ground up way to avoid circular logic, to make sure that like the theory itself is actually sound, okay? But like usually, if you're just analyzing some random series, right, chances are like using the integral test on it is not going to cause some kind of like circular logic, right? Okay, so generally speaking, I wouldn't have a problem if you decided to invoke the integral test in a proof, okay? However, if you really want to like, be super careful and not use the integral test for now, at least until we define what integrals are, right? I want to show you something, okay? Because I think this actually kind of gets at a deeper, it's kind of a deeper skill in math, right? Which is kind of like doing this balancing act between sort of the respecting the rigor and formalism of proofs and the kind of like more blurry and kind of like rough-handed problem-solving process that actually leads us to formulating those proofs, okay? Like remember when we were doing like convergence of sequences and stuff like that, there would kind of be this like scratch work part, and then like, at least the way I would do it, I would always kind of do the scratch work first, and then I would kind of like lay out the proof all very carefully, okay? That's kind of one example of this kind of thing where there's a relationship between just like your raw intuition about things and the proofs you write, right? Which is that like, you want to use every piece of intuition or whatever, any information you have at your disposal, any tools you have at your disposal, you want to use all of that stuff to figure out what you think is really going on in a problem, right? So for example, figuring out whether a series converges, right? Just making that one binary determination for yourself in your head, right? Figuring out what you believe about a series. You can use the integral test to do that, and no one's going to like prosecute you for it, right? I mean, you don't have to put it in your proof, but you can use it to get to that piece of knowledge. And then once you get to the point where you know whether the series converges or diverges, then you can kind of go back and formulate a proof, using different things if you really want to. Or, I mean, not that I think using the integral test would be bad, but if you really want to be careful, you can go back and, use different logic. So like, let me just give you one kind of example of this, and I'll try to keep this relatively brief. But we were looking at the situation of, so consider the series of 1 over n squared, right? The integral test showed us that the series from k equals 1 to n of 1 over k squared is less than or equal to 1 plus the integral from 1 to n of 1 over x squared dx, which equals 2 minus 1 over n, okay? So now, given that since all the terms here are positive, right, if we wanted to show this series converged, regardless of whether we were using the integral test or not, one way to do it would be simply to bound it above by some positive number, because if all the terms are positive, that means the partial sums are increasing, right? So it's a monotonic sequence. So if you bound it above, then that guarantees that monotonic sequence will converge. So that guarantees the series will converge. So now what I want to point out to you is that, like, okay, maybe we used the integral test to find this bound. But now that we have the bound, it doesn't matter that we got it by using the integral test, right? The integral test in this case, if you really want it to, can function purely as a heuristic. And now that you have this bound, you can actually prove this bound directly, okay? So we can prove directly that the integral from 1, or sorry, not the integral, that the sum from k equals 1 to n of 1 over k squared is less than or equal to 2 minus 1 over n. And this would be enough to show that the series from k equals 1 to infinity of 1 over k squared converges, right? So what I'm telling you is that like the integral test can be this useful auxiliary tool in the background, but then you can toss it out once you've gotten whatever you need out of it, right? And you can make your proof not rely on that if you really want to. And this is like a general thing in math, right? Like, and especially in analysis, is that you want to just use whatever kind of like instincts that you develop to estimate things, or kind of get any kind of like rough idea of what's going on in some complicated expression or problem or whatever, right? Anything you have at your disposal you can use that can guide you in formulating a proof which is actually rigorous. Okay, so the real skill is like turning your instincts into a rigorous proof, right? So in this case, one thing that we could do is just by induction, prove this by induction. So the base case is pretty obvious, okay? So let's suppose this is true for some particular value of n. So suppose this is true for some n. Then the sum from k equals 1 to n plus 1 of 1 over k squared is less than or equal to 2 minus 1 over n plus 1 over n plus 1 squared, right? I used the bound here, the inductive hypothesis, I used it to bound the first n terms above, and then I have one term left over when k equals n plus 1. So that's what this is, right? Now what I want is, so the question is this less than or equal to 2 minus 1 over n plus 1 squared, right? And that's equivalent to, well, to the question. So the question of whether this is less than or equal to this is equivalent to the question of, so this is kind of like side work also, of whether, right, this thing that's being subtracted here, which is 1 over n minus 1 over n plus 1 squared, is bigger than 1 over n plus 1 squared. So the question is 1 over n minus 1 over n plus 1 squared bigger than or equal to 1 over n plus 1 squared, aka is 1 over n bigger than or equal to, so this is a question we're asking, right? Is the 1 over n bigger than or equal to 2 over n plus 1 squared, right? Or in other words, is n plus 1 squared bigger than or equal to 2n? And clearly this is, because on this side we have n squared plus 2n plus 1, right? So basically, this logic here implies that this inequality is true, right? And so then that completes the inductive step, right? So if you kind of reverse this logic, right, you start with this fact that n squared plus 2n plus 1 is greater than or equal to 2n, so n plus 1 squared is greater than or equal to 2n, you flip it all around, so then this is bigger than this, so then 2 minus this is less than or equal to 2 minus this. That's how you get here, okay? And so that proves the bound, right? And look, the integral test was nowhere to be seen in this proof, even though we did use it to actually come up with this bound in the first place, right? It's kind of the reverse of how, like in like legal contexts, like when you're prosecuting a criminal, there are rules about how you can obtain evidence. So like if you come up with evidence that like totally 100% incriminates someone, your case can still be completely invalidated by like having obtained the evidence illegally, right? Even if the evidence is like extremely good. This is the exact opposite. You can obtain your evidence however you want, and as long as it's valid, that's all that matters in the end, right? You can obtain your logic. You can arrive at your logic by whatever means you want. I mean, we could just as well have arrived at this proof by like, using tarot cards and a divining rod or whatever, right? And if this was what we ended up writing down, it wouldn't change that this is a valid proof. We would have just used a terrible method to come up with it. And it would be really unlikely, obviously, to come up with a successful proof if you're using something that doesn't work. But so in this case, it's like we know the integral test works, we just haven't proved it yet. So that's why we have faith that this should all work out, and indeed it does, okay? I just wanted to cover that just because like it really is, it's a very broad skill that you can develop as a mathematician to start to go about solving problems this way, to develop this like, there are two sides of your abilities. There's the formal proof side, but there's also just this kind of instinctive side where you try to like analyze things using all of the skills and tools and tricks that you have at your disposal. So in the next video, I will talk about the alternating series test, and I think that should do it for this lecture.